This is the solution for a question covering the sublearning outcome. Calculate net force on a 2D rigid body using free body diagram and equilibrium equation from Mechanic 1. In this question, there are 4 unknowns, but there are only 3 equilibrium equations, which is impossible to solve this question. Therefore, we need to break the system up. Remember, don't calculate the force equivalence before you break the system up, because if you find the point load first, the point load will only appear on one side of the system after you break it, which is not true. We will break the system at point D, which is a pin connection as shown below. We will then identify all the reaction forces at each point. Point A is a pin support. It has both reaction forces in the X and Y directions. Point B and C are roller support. There will be only one reaction force acting normal to the surface, which is in the Y direction. We know that point D is a pin connection, therefore it reacts in both X and Y directions. This set of forces are different from those in the other half of the system. They are equal in magnitudes but opposite in direction. We assume that the forces on the right side of the system are acting upward and to the right, while the forces on the left side are acting downward and to the left. Remember, it doesn't matter which side you assume up or down. We will start the calculation with the right side of the system. We need to find the equivalent single point load first. -2 kilonewtons per meter multiplied by the length of the distributed load, which is 6 meters. Negative because the forces are acting in a downward direction. We get the point load equals to -12 kilonewtons. Then, to find the location of the point load, we take 6 meters divided by 2, which is 3 meters. We will draw the force pointing downward on the diagram because the force we got is in negative. We will draw a coordinate system with positive pointing upward and to the right, and positive moments rotating counterclockwise. To find a vertical reaction at point C, we will need to take the moment about point D, which must equals to 0 in equilibrium. -12 kilonewtons multiplied the perpendicular distance from point D, which is 3 meters. Negative, because it is causing a clockwise moment about point D, plus positive Cy multiplied by 6 meters. Positive, because it is causing a counterclockwise moment about point D. Rearrange the equation, we get the vertical reaction at point C equals to 6 kilonewtons. Next, we are going to calculate the reaction at point D. We will set up an equilibrium equation for the net force in X direction that must equals to 0. There is no other force in this question that is acting in X direction other than dx. Therefore, we get dx is equals to 0 kilonewton. We will set up another equilibrium equation for the net force in the Y direction, which must equals to 0, which equals -12 kilonewtons, negative because the force is acting in the downward direction, plus positive Cy, which is 6 kilonewtons, positive because the force is acting in the upward direction, plus positive dy, positive because we assume it is acting in the upward direction. Rearrange the equation, we get dy is equals to 6 kilonewtons. Now we can move on to the left side of the system. To calculate the equivalent single point load, we take -2 kilonewtons per meter multiplied by 4 meters. Negative because the forces are acting in a downward direction. We get the point load equals to -8 kilonewtons. Then we take 4 meters divided by 2, which is 2 meters. We will draw the force pointing downward because the answer we got is in negative. Recall from the right side of the system, we have found dx equals to 0 kilonewton and dy equals to 6 kilonewtons. Remember, the set of forces are equal in magnitude but opposite in direction. So we don't need to change the sign of the force when calculating for the other side of the system, because we already draw the force on the diagram in the opposite direction. To find the vertical reaction at point B, we will take the moment about point A that it must equals to 0, which equals positive By multiplied by 10 meters, positive, because it is causing a counterclockwise moment about point A, plus -8 kilonewtons multiplied by 12 meters, negative, because it is causing a clockwise moment about point A, plus negative dy, which is 6 kilonewtons, multiplied by 40 meters, negative, because it is causing a clockwise moment about point A. Rearrange the equation, we get By is equals to positive 18 kilonewtons. Now we set up an equilibrium equation for the net force in x direction to find Ax, that it must equals to 0, which equals positive dx, which is 0 kilonewtons, plus positive Ax, positive, because we have assumed the reaction force are acting in the positive direction. Rearrange the equation, we get Ax is equals to 0 kilonewton. Next, we will set up another equilibrium equation for the net force in the y direction that must equals to 0, which equals positive By, which is 18 kilonewtons, positive, because it is acting in an upward direction, plus negative dy, which is negative 6 kilonewtons. It is negative here because it is acting in a downward direction, plus negative 8 kilonewtons, negative because it is acting in a downward direction, plus positive Ay, positive, because we assume that Ay is acting in an upward direction. Rearrange the equation, we get the answer for Ay is equals to negative 4 kilonewtons, which means our assumption for Ay pointing upward is wrong. The answer is telling us that Ay is a force that is acting in a downward direction. In this question, we have identified the support at point A, B, and C. They are pin support, roller support, and roller support. We have found the reaction forces at A, B, C, and D, which Cy equals to 6 kilonewtons, dx equals to 0 kilonewton, dy equals to 6 kilonewtons, by equals to 18 kilonewtons, ax equals to 0 kilonewton, and ay equals to negative 4 kilonewtons. We have also found the equivalent single point load. Remember, don't calculate the point load before breaking the system up. It will result the force only appearing on one side of the system, which is not true. Remember that if you break the system up, the set of forces will be equals in magnitude but opposite in direction.